National Electrical Code, or NEC, recommends ground fault circuit interrupter, or GFCI, protection for outlets located within 6 feet of laboratory sinks. The interpretation that the 6-foot rule does not apply if the outlet is at a 90-degree angle from the sink is incorrect. The 6-foot rule is irrespective of the angle of the outlet to the sink. The 6-foot rule for GFCI protection is based on the assumption that water can splash or spill from the sink and reach outlets within that 6-foot distance. It is not directly related to the length of a standard extension cord. Instead, it addresses the potential for water exposure near electrical outlets. GFCIs protect against electrical shock by interrupting power to the outlet if it detects an imbalance between the incoming and outgoing current. This imbalance can occur when water comes into contact with an electrical appliance or outlet, or when a person touches both a live wire and a ground source. In a laboratory setting, water is a regular occurrence around sinks. Electrical appliances, such as hot plates or stirrers, may be plugged into outlets near the sink. GFCI protection ensures that power is interrupted if water makes contact with any electrical equipment, minimizing the risk of electrical shock. Now let's delve deeper into GFCIs, examining their function, code compliance, and practical applications in laboratory settings. A GFCI, or ground fault circuit interrupter, is a safety device designed to protect individuals from electrical shock. It constantly monitors the current flowing through a circuit. If it detects an imbalance between the outgoing and incoming current, it quickly interrupts the power supply. This imbalance typically indicates that current is leaking to ground, potentially through a person who is in contact with a live wire. The NEC, a widely adopted standard for electrical installations, specifies when and where GFCI protection is required. Its purpose is to minimize the risk of electrical hazards and ensure safety. Article 210.8 within the NEC covers GFCI protection for personnel. It outlines specific locations where GFCI protection is mandatory, including bathrooms, kitchens, garages, and outdoor areas. The code provides detailed requirements for dwelling units, but it also addresses GFCI protection in commercial and industrial settings, such as laboratories. Now, let's focus specifically on laboratory settings. The NEC does not explicitly single out laboratory sinks as requiring GFCI protection in every situation. However, the code does mandate GFCI protection for receptacles located within 6 feet of sinks in dwelling units. This requirement is based on the increased risk of electrical shock in areas where water is present. Because laboratories often involve water and electrical equipment, it is best practice to extend the GFCI protection requirements to lab sinks as well. Let's consider several key aspects when determining whether GFCI protection is necessary for outlets near lab sinks. Firstly, the proximity of the outlet to the sink is crucial. As mentioned earlier, the NEC specifies a 6-foot distance for dwelling units. This distance is a reasonable guideline for laboratories as well. If an outlet is located within 6 feet of a sink, it is highly recommended to provide GFCI protection. Secondly, the potential for water exposure must be assessed. Laboratories often involve experiments and procedures that can result in splashing or spills. If there is a likelihood that water could come into contact with electrical outlets or equipment, GFCI protection is essential. Thirdly, the types of equipment used near the sink need to be considered. If electrical appliances, such as hot plates, stirrers, or water baths, are frequently used near the sink, the risk of electrical shock increases. GFCI protection is particularly important in such cases. Now let's discuss some practical considerations for implementing GFCI protection in laboratories. Firstly, GFCI receptacles can be installed directly in place of standard outlets. These receptacles have a built-in GFCI that trips when a ground fault is detected. They are easy to install and provide local protection at the point of use. Secondly, GFCI circuit breakers can be used in the electrical panel to protect an entire circuit. This approach provides protection for all outlets and equipment connected to that circuit. GFCI circuit breakers are more expensive than GFCI receptacles, but they offer broader protection. Thirdly, portable GFCIs are available for temporary use. These devices plug into a standard outlet and provide GFCI protection for any equipment plugged into them. Portable GFCIs are useful for situations where permanent GFCI protection is not feasible. When installing GFCI protection, it is important to follow the manufacturer's instructions and all applicable electrical codes. It is also crucial to test the GFCI regularly to ensure that it is functioning properly. GFCIs should be tested monthly by pressing the test button on a device. If the GFCI does not trip, it should be replaced immediately. In addition to GFCI protection, several other safety measures can help prevent electrical shock in laboratories. Firstly, all electrical equipment should be properly grounded. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. Secondly, electrical cords and equipment should be regularly inspected for damage. Damaged cords or equipment should be repaired or replaced immediately. Thirdly, wet hands or surfaces should never be touched when operating electrical equipment. Water is a conductor of electricity, and it can significantly increase the risk of electrical shock. Fourthly, electrical equipment should be kept away from water sources whenever possible. If equipment must be used near water, it should be placed on a non-conductive surface and protected from splashes. Fifthly, laboratory personnel should be trained on electrical safety procedures. Training should cover topics such as GFCI protection, grounding, cord inspection, and safe work practices. Now, let's consider some specific scenarios where GFCI protection is particularly important in laboratories. Firstly, when using electrical equipment near sinks, such as hot plates or stirrers, GFCI protection is essential. These appliances can easily come into contact with water, creating a significant risk of electrical shock. Secondly, when performing experiments that involve conductive liquids, such as saline solutions or acids, GFCI protection is crucial. These liquids can create a path for current to flow to ground, potentially through a person. Thirdly, when working with equipment that has exposed electrical parts, such as open chassis power supplies, GFCI protection is highly recommended. These parts can pose a shock hazard if they come into contact with water or a person. Fourthly, when using extension cords in the laboratory, GFCI protection is advisable. Extension cords can be easily damaged or overloaded, increasing the risk of electrical shock. Now let's address some common misconceptions about GFCI protection. Firstly, some people believe that GFCI protection is only necessary in wet locations such as bathrooms or kitchens. However, GFCI protection is also important in any location where there is a risk of electrical shock, regardless of whether the location is wet or dry. Secondly, some people think that GFCI protection is only necessary for 120-volt circuits. However, GFCI protection is also available for 208 volts, 240 volts, 277 volts, and 480-volt circuits. Thirdly, some people believe that GFCI protection is a substitute for grounding. However, GFCI protection and grounding are both important safety measures, and they should be used together. Grounding provides a path for fault current to flow back to the source, while GFCI protection interrupts the power supply when a ground fault is detected. Now, let's discuss some of the limitations of GFCI protection. Firstly, GFCIs do not protect against overload or short-circuit conditions. Overload and short-circuit protection are provided by circuit breakers or fuses. Secondly, GFCIs do not protect against line-to-line contact. GFCIs only detect ground faults, which occur when current leaks to ground. Thirdly, GFCIs can nuisance trip, which means that they can trip even when there is no actual ground fault. Nuisance tripping can be caused by electrical noise, faulty equipment, or other factors. In summary, GFCI protection is an essential safety measure in laboratories, particularly near sinks. The NEC recommends GFCI protection for outlets within 6 feet of sinks in dwelling units, and this recommendation should be extended to laboratories as well. GFCI protection protects against electrical shock by interrupting power to the outlet if it detects an imbalance between the incoming and outgoing current. When implementing GFCI protection, consider the proximity of the outlet to the sink, the potential for water exposure, and the types of equipment used near the sink. GFCI receptacles, GFCI circuit breakers, and portable GFCIs are all available for providing GFCI protection. In addition to GFCI protection, other safety measures such as grounding, cord inspection, and safe work practices can help prevent electrical shock in laboratories. Let's now consider the specific requirements and interpretations of the National Electrical Code related to GFCI protection around sinks, focusing on the nuances that might apply to a laboratory setting. The NEC, specifically Article 210.8, addresses GFCI protection. The language in this article is constantly evolving with each new edition of the NEC to address gaps in safety. It's crucial to consult the latest edition of the NEC to ensure compliance with the most current requirements. While the NEC provides specific rules for dwelling units, the application of these rules to commercial or industrial settings like laboratories requires careful consideration and often interpretation by qualified electrical professionals. The facility staff's interpretation regarding the 90-degree angle is incorrect because the NEC specifies a distance, not a direction. The 6-foot rule is a radius extending from the sink's edge, not a line. This means that any receptacle within that circular area needs GFCI protection, regardless of its orientation to the sink. The rule is primarily concerned with accessibility and the likelihood of water reaching an outlet, regardless of the direction. It is based on the assumption that water can splash or spill in any direction. The rule is rooted in practical experience and statistical data regarding electrical accidents in wet environments. It is not directly linked to the standard length of extension cords or the precise expected splash distance, although these factors might have influenced its establishment. The 6-foot distance is a reasonable compromise between providing adequate protection and minimizing unnecessary tripping in normal use. The fundamental reason for GFCI protection is to mitigate the risk of electrical shock. Normal circuit breakers protect against overloads and short circuits, preventing fires and equipment damage. GFCIs, on the other hand, detect ground faults, which are leakages of current to ground. These leakages can be dangerous because they can pass through a person who is in contact with both an electrical source and a grounded object, such as a metal sink or plumbing. GFCI protection is designed to interrupt the circuit very quickly, typically within 20 milliseconds, when a ground fault is detected. This rapid interruption minimizes the duration of the shock and significantly reduces the risk of serious injury or death. The activation threshold for GFCI is very low, typically 5 mA. This means that it can detect and respond to current leakages that are far below the level that would trip a standard circuit breaker. This sensitivity is crucial for providing effective protection against electrical shock. In a laboratory setting, several factors increase the potential for electrical hazards around sinks. Firstly, laboratories often involve the use of water and other conductive liquids, which can increase the risk of electrical shock if they come into contact with electrical equipment or wiring. Secondly, laboratories typically have a higher density of electrical equipment than other environments, increasing the probability of ground faults. Thirdly, laboratory personnel may be working with complex and potentially hazardous electrical equipment, which requires a higher level of safety protection. Given these factors, it's important to take a conservative approach to electrical safety in laboratories. Even if the NEC does not explicitly require GFCI protection in a specific situation, it is often prudent to provide it as an additional layer of safety. It is also crucial to implement a comprehensive electrical safety program that includes regular inspections, employee training, and proper maintenance of electrical equipment. Now let's think about specific examples. If a lab uses a recirculating water bath near the sink, the risk of water splashing onto nearby outlets is significant, warranting GFCI protection. Similarly, if researchers are frequently cleaning glassware or equipment near the sink, the potential for water exposure increases. If the laboratory conducts experiments involving electrolytic solutions, such as salt water or acid solutions, the risk of electrical shock is elevated, and GFCI protection becomes even more critical. The type of research being conducted also plays a role. A chemistry lab dealing with corrosive chemicals might have a higher risk of spills affecting electrical components compared to a dry biology lab. Laboratories should conduct a thorough risk assessment to identify potential electrical hazards and determine the appropriate level of protection. This assessment should consider the types of equipment used, the procedures performed, the presence of conductive materials, and the training and experience of the personnel. While the NEC is a valuable resource, it is not a substitute for sound engineering judgment and a comprehensive understanding of electrical safety principles. Qualified electrical professionals should be consulted to ensure that electrical installations in laboratories meet all applicable requirements and provide an adequate level of protection. Proper grounding is also a key component of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. All electrical equipment in the laboratory should be properly grounded in accordance with the NEC. Grounding conductors should be regularly inspected to ensure that they are intact and properly connected. The 6-foot rule may seem arbitrary, but it represents a practical balance between safety and usability. It is important to understand the reasoning behind the rule and to apply it thoughtfully in the laboratory setting. Remember that the primary goal is to protect personnel from electrical shock. If there is any doubt about whether GFCI protection is needed, it is always best to err on the side of safety and provide it. Regular testing of GFCIs is crucial. Test them monthly to verify they are functioning correctly. Simply press the test button and the GFCI should trip, interrupting the circuit. If it doesn't trip, replace it immediately. Labs should also have a documented electrical safety plan, including training for all personnel who work with electrical equipment. This training should cover the proper use of equipment, identification of hazards, and procedures for responding to electrical emergencies. Review these plans regularly and update them as needed. Consider using additional safety measures such as insulating mats in wet areas and regularly inspecting electrical cords for damage. Don't overload circuits with too many devices. Use power strips with built-in overload protection. Replace damaged cords immediately and avoid using extension cords as permanent wiring. Remember, electrical safety is an ongoing process, not a one-time fix. Vigilance, training, and adherence to best practices are essential for maintaining a safe laboratory environment. Now let's talk about the specific types of equipment that might be used near a laboratory sink and how they relate to the need for GFCI protection. Consider a hot plate used for heating solutions. If a spill occurs, the water could easily enter the hot plate's internal components, creating a shock hazard. GFCI protection would quickly cut off the power. Magnetic stirrers are another common piece of equipment. While they might seem less risky, spills can still damage the motor and electrical components, leading to potential shocks. A water bath, used for maintaining samples at a constant temperature, presents an obvious water hazard. GFCI protection is crucial in this scenario. Even seemingly innocuous equipment like pH meters or conductivity meters can pose a risk if they are dropped into water or if their power cords are damaged. In addition, consider equipment with metal housings. If a fault occurs and the housing becomes energized, a GFCI can prevent a shock if someone touches the housing and a grounded object. It is also important to consider the cleaning procedures used in the lab. If lab personnel regularly wash equipment near the sink, the potential for splashing and water exposure increases. This is especially true if pressure washers or spray nozzles are used. The design of the sink itself can also play a role. A deep sink with high sides is less likely to cause splashing than a shallow sink with low sides. The presence of a drain board can also affect the risk of water exposure. If the drain board is close to electrical outlets, GFCI protection becomes even more important. Consider the age and condition of the electrical wiring in the lab. Older wiring may be more prone to insulation breakdown and ground faults. Regularly inspect the wiring and upgrade it as needed. Pay attention to the type of outlets used in the lab. Tamper-resistant outlets are recommended, especially in areas where children or untrained personnel may be present. These outlets have a mechanism that prevents objects from being inserted into the slots, reducing the risk of electrical shock. In addition to GFCI protection, consider using arc fault circuit interrupters or ASIs in the lab. ASIs detect arc faults, which are a common cause of electrical fires. They can provide an additional layer of protection against electrical hazards. Remember that the goal of electrical safety is to create a safe working environment for everyone in the lab. Take the time to assess the risks, implement appropriate safety measures, and train personnel on safe work practices. It is vital to consult with qualified electrical professionals to ensure that the electrical system in the lab meets all applicable codes and standards.